So when dealing with vector subspaces, um, well, there's a core difference between subspaces and subsets. And this video is going to deal with one of the technical things that appears when you want to, do more set theory stuff. So maybe I should just be specific. In set theory, you have operations like union and intersection, and intersection is perfectly well behaved for vector spaces. If you have two vector subspaces of a vector space, the intersection is again a perfectly good subspace. Fine. The difficult thing is that in general, the union of two spaces is just about never a vector space. And the reason we can kind of see it if we just think about like Euclidean spaces, right? Like here's a line, right? They're part of the larger R2. I don't know how to draw this. Sorry. I'm saying I just am interested in the union of the two lines and by themselves. This is not going to be a vector space anymore because if I take anything in one line and add it to anything in a different line, I get something not in either one of them. So this doodle sucks. I'm sorry. But hopefully that motivates the following definition, which is a way of, well, sort of fixing this problem. Given V1 through Vn, subspaces of a vector space V, we define V1 plus V2 plus and so on up to Vn to be the set of sums that you get, V1 of little v's, where each little v belongs to his corresponding big V. And so, in other words, what this means is take all sums of elements of each VI. And so that fixes the problem we had in the previous guy, where if I want to take a quote union unquote of the x-axis and the y-axis, well, on the nose, it doesn't work. But if I take the sum, according to this definition, then now I'm allowed to combine those elements in different spaces. And then I add them in the big vector space. So life is good. The first thing that I want to do is show one of the examples from Axler that I think is worth seeing because you would be right if you said, okay, your definition is fine and cool, but I feel like in practice, I don't know that I understand what it looks like. I want to show you how to figure out a description from this partial information. So let's say we're working in over a field F, and we're looking at subspaces of F4. I can put, here's one subspace, U, which has elements of the form X, X, Y, Y. So in other words, the first two components are equal. And then we can also have a V, which has the first three components equal. Then the question is, what is U plus V? Can I describe U plus V? And the easiest way to do that is to start by just picking some elements and trying to add them and see what you notice. So maybe if I take an element of U, A, B, B, and then I add it to an element of V, like this, what do I get? I get A plus C, B plus C, B plus D. So these two, still same. These two look totally arbitrary to me. And so looking at inspecting this equation, I might suspect that U plus V can be described as stuff of the form X and X, first two the same, Y and Z, last two could be anything. So now I want to prove that. In order to prove it, I have to use the definition. I have to show that if let's call this thing let's call this S. I will show that U plus V is a subset of S, and also U plus V contains S, and therefore they're equal. That's our plan. So one of these things I've kind of already done, right? I just showed that if I take an element of U plus V and I add them together, I get something where the first two coordinates are equal. And so this proves that this is inside S. Now what I have to do is prove that everything in S can be decomposed into U and V. So in other words, I have to prove S is a subset of U plus V. So here's how I'm going to do that. Let's say I have an element XX, Y, Z in S. In U, the first two things are equal. So how about I start with X and X, and then I start with Y and Y? Well, what if I start with X, X, Y, Y, what am I missing to get this particular vector? Well, these guys are already right. This guy's already right. Here I have Z minus Y, right? I've subtracted off Y from Z. And then you notice that this lives in U and this lives in V. And that's what I wanted to prove. So we successfully decomposed S into U plus V. Okay, there is a proposition in Axler which is basically just unraveling the definitions. So I'm going to leave it to you to read. That the sum of two spaces, or it could be any number of spaces, is the smallest subspace of V containing each of the V's. I'll just say VI, all the VI. What I want to do is turn our attention to the direct sum. Direct sum is a refinement of the sum, which we are often grateful to see. In particular, our definition of direct sum is as follows. We suppose that V1 through Vn, Vm, let's follow his notation, are subspaces of V. We will call V1 plus and so on up to Vm direct. If every element of V1 plus Vm is expressed uniquely. And in that case, we will write V1, and then we'll write this O plus symbol instead to emphasize that it's a direct sum. So the reason that we like this idea of expressing things uniquely is important is because, well, what if there are like multiple different ways of doing things and you want to know that your math is, well, correct? In this situation, this would look to me like an example of a direct sum. I'm looking this over and I'm failing to see how one could do any better than this. Could one have done this differently? If I tried like XX, ZZ instead, then it would be this component. So yeah, this looks right to me. So this example that we tried to smuggle in here seems to be a direct sum. But we could see sums that are not direct. And let's try to understand a little bit an example to see why this might be a little bit painful. So let's consider in F3, let's set V1 to be the sort of XY plane, if you will. Right, third component 0. Then we'll look at the Z axis. And then let's say we throw in something else. Like this random plane, or sorry, this is a line, one free parameter, that's kind of diagonal. So we can try to draw this thing. So here's V1, here's V2, and then if we have X, Y, Z, then this thing here, V3 is just going this way, right? In this sort of YZ, I don't know how clear it is that I'm trying to draw. Like this is the 45-degree angle in this vertical plane. So this is a direct sum. V1 and V2 give a direct sum. V1 plus V2 equals F3, right? Everything in F3 can be written as something in the plane and some Z amount, and it can be done uniquely, as you guys believe. On the other hand, it's pretty far from a direct sum if you allow this V3, because just think about the 0 vector. How many ways could I write just 0? Well, I could start by writing, some 0, 0, 0 plus 0, 0, 0, right? This in V1, this is in V2, plus 0, 0, 0 in V3. Of course I could do that. But what about, I don't know, 1, 2, 0 in V1 plus 0, 0, 2 in V2. Sorry, I can't put a 1 here. I have to put a 0 here. What I said wasn't going to be right. Plus 0 minus 2 minus 2. If you add those things up, right, this is still 0. So we see the non-uniqueness. Not of the vector, of course, but of the representation. And so one can understand how this could be annoying. When we want to talk about like referring to vectors, we want to do so in an unambiguous sort of way. And so sums that are not direct have this feature of, well, frankly, kind of being obnoxious. And so we're going to be on the lookout for this. What I've said here is pretty close to a proof of the following proposition. So let's write down this proposition and then inspect the proof. This is the condition for a sum to be direct. So we suppose V1 through Vm are subspaces of V. Excuse me. Then V1 plus V2 and so on is equal to the direct sum, right? In other words, the sum is direct. If and only if the only representation of 0 is all little vi equals 0. In other words, there's no non-trivial relationship between the vi's. Okay, so let's take a look at how we prove this. for the first direction, we suppose that it is in fact a direct sum, right? Assume direct sum. Then actually there's nothing to prove here because being a direct sum meant that every vector has unique representation. Unique representation. This representation of all the VI's being 0 is, of course, available to us always. And so since the representation is unique, that must be the only one. So we're done. In particular, no non-trivial representation for 0. Let's take a look at the other direction. For this way, I have to suppose that the only way to write 0 is by adding up a bunch of zeros. And now I need to show that the sum is direct. So, in other words, I need to prove any V in V1 plus Vm has a unique representation. Well, here's how we can do that. Suppose not. Suppose that V has two non-trivial representations. At this point in time, I want to introduce some notation. I want to... Do I want to use this notation? Yeah, what the heck, right? Let's do it. We're going to use big sigma notation. Right? AI, VI means add up some AIs times some VIs, right? This sigma notation means add up the things. The AIs are numbers, the VIs vectors. So if I can write this in two non-trivial ways, then I can write V as a sum of some VIs, where each VI lives in big VI. And then I'm saying, suppose I have two representations. So I also have, for some different choices of A's and, some different choices of constants and some different vectors, right? Because these vectors could be anything. They just live, each one lives in its respective vector space. That's all I know. What I can do is then write 0 equals V minus V equals add up the VI's minus what you get when you add up the UI's. And so what this gets me is actually a sum of the form AI VI minus BI UI. In other words, I'm just regrouping all these together because each of these things lives in VI. But you see, now we have a problem, which is that I was assuming that 0 has a unique representation. If the representation of 0 is that the only way to have this is for all these things to be 0, then it must be that AI VI minus BI UI equals 0. That in turn is the same thing as saying AI VI equals BI UI. And of course, then, the only way that this can be is if all of these things are 0. Or rather, all these things are equal on the nose, I guess is what I should say. Right. Okay, how long have we been going? 20 minutes. Oh, so long. Okay, I have one more fact, and then I promise I'll keep this one quick. Just an extremely useful fact to know. If U and V are subspaces of a vector space, u plus v is direct if and only if u intersect v consists only of the zero vector. And this is a consequence of where we were just at. So again, we have two directions. First, we assume that u plus v is direct. Well, if this is a direct sum, and I put any, let's say we take some vector v in u intersect v. Well, of course, 0 is always in this intersection, right? Just because 0 lives in every vector subspace. And also 0 is always equal to v plus minus v. On the other hand, if v is in u intersect v, then I regard this thing as living in v and this thing as living in u, or the other way around. I guess it doesn't matter. And that gives a non-trivial representation of 0, which I'm not supposed to have. And so therefore, this is a contradiction, or maybe said the other way around, is I could think of this as a proof of the contrapositive. Namely, if there's anything not 0 in here, then this construction shows that this sum is not direct. Let's go the other way. We assume that the intersection consists only of 0. And now I need to prove that the sum is direct. So let's say I take any two elements just in u and v respectively. So I have a little u plus v. This thing will then live in u plus v. And I want to know, could this thing equal 0? In order to finish the proof off, what I should do is show that this implies u and v respectively are both equal to 0. Of course, though, this equation tells me that u is equal to minus v, and we know that our subspaces are closed under taking things like additive inverses. So this implies that since v is the additive inverse of u, v must be in u's space. In other words, this thing can't be true unless these were already equal to 0. And that finishes our proof off. All right, friends, thanks for being patient with me. Sorry this took a little bit longer than I wanted it, but I think hopefully we all survived. What you will find as you look at the homework is we have selected up problems whose sole purpose is to illustrate all of this. I was realizing as we were getting to the end of this chapter that, well, if you don't already know something about vector spaces and linear equations, probably you're more than itching for some problems. And so take a look at those. And if anything should come up, you feel like you're stuck, well, our discussion groups still exist on Canvas, and so you can find me over there. All right, friends, I'll see you all in the next one. Until then, take care.